Hey. Thanks very much, Peter. I was very mindful of the fact that this title is one that I think many people in the room have heard me talk about before. While I am going to talk about this title, I hope I can spend most of my time telling you about some work that is not published yet and that I don't think we've really presented before. I do want to thank Peter and Nick and the organizers for inviting me here. It's been a really exciting meeting. Well, the physiome, I think, involves integration of three types: data integration, functional integration, and structural integration. And data integration we achieve with bioinformatics, and functional integration is the goal of systems biology. But really what I want to focus on is structural integration, which is the realm of multi-scale modeling, and I think most of the modeling that we'll be hearing about in this session. And particularly the work of three students, Sarah Flame, who did some of the electrophysiology work before she came to Oxford to do a postdoc. Roy Kirchhoffs, who did some of the mechanics. But almost all my time, actually, I'll be spending talking about the work of Stuart Campbell on excitation-contraction coupling, but actually more specifically on the calcium contraction side of excitation-contraction coupling rather than the excitation-calcium side, which is what we mostly hear about when we talk about excitation-contraction coupling. The elements of our coupled electromechanical models of the ventricles have included the ion currents, calcium handling mechanisms, myofilament activations, cross-bridge interactions at the level of the cell, impulse propagation, and myocardial mechanics at the level of the tissue, whole ventricle electromechanics coupled to some systems models of the circulation. Like I say, I'll show you a little bit of this, but I really want to focus on this part of the story, which relative to the others I think has been a little bit neglected. This work starts really with a model that Sarah published in AJP with a lot of help from Wayne Giles of the canine ventricular myocyte, the purpose of which was to see if we could understand better the ionic basis of the transmural differences in the action potential morphology and its rate dependence. And in order to do that, we were fortunately able to make use as a starting point of the excellent model of Joe Greenstein and Ray Winslow. But in order to adjust that model, which was a canine mid-myocardial cell model for the epicardial cells and the endocardial cells, we had to make some important changes. We had to change the model of the sodium channel to a Markov model so that we could represent the late component of the sodium current, which turns out to be different enough to affect the action potential duration and its rate dependence significantly. And for that, we made use of the sodium channel model that Colleen Clancy developed originally with Yoram Rudy. The other thing we had to do is introduce a Markov model of the ITO current of the KV4.3 current and its modulation by K-chip, again to properly represent the transmural differences in the transient outward current between the epicardium, where it's quite strong on the dog, and the endocardium, where it's quite weak. Finally, we had to make some parameter adjustments to the handling of the SR calcium ATPase pump current and the delayed rectifier potassium currents. I'm not really going to talk about that work other than to comment a little bit on the calcium transients, because of course this is the link to contraction. So here's the action potentials, and their morphology and their rate dependence looked pretty good and showed good agreement with experiments. Here are the calcium transients. And I should say that it turned out that most of these transmural differences were explained not by differences in delayed rectifier potassium currents, but in the late sodium current and in the transient outward current. So those earlier currents turned out to be more important in shaping the transmural differences of the action potential than the later currents. And really that you could see that just by looking at the action potential, because the big differences are really in the earlier part of the plateau, not the last part. But also, those currents, particularly the transient outward current, turned out to be important in modulating the calcium current, and that in turn affected the release of calcium from the sarcoplasmic reticulum, such that there are large differences, amplified when we took into account differences in the circuit pump activity, between the epicardial and endocardial and mid-myocardial calcium transients with respect not so much to their amplitude, but their timing. So you can see that, that there's a much slower rise time of the calcium transient on the endocardial cells and on the epicardial cells, which were faster. Okay. And that actually could serve a functional purpose, because under normal physiological conditions, the endocardium is going to be depolarized first, and so this could help the synchrony of contraction by compensating for the transmural activation delay in the normal myocardium. And in fact, this model, if we looked at particularly the timing parameters of the calcium transients, showed remarkably good agreement with experiments. So this wasn't, we weren't fitting this model to these experiments, but the experimental measurements of transmural differences in the time courses of calcium transients were actually quite well captured by this model. So we thought, okay, now we're ready to go to work and make it a coupled electromechanical model that incorporates these transmural heterogeneities, and all will be well. Fortunately, there were some experimental data on transmural heterogeneities in twitch dynamics that we could use to validate a model that coupled calcium to contraction. And these were done in Charlie Anselevich's lab by Jonathan Cordero. And you can see that corresponding to those differences in the calcium transient, the epicardial myocytes, this is unloaded cell shortening, shortened faster and reached peak shortening much sooner than the endocardial myocytes, which had a much slower time to peak. So the question was, are these differences in shortening dynamics explained entirely by these differences in calcium transient dynamics? And so in order to do that, we used Jeremy Rice's recent model to couple the calcium transients to the, shown here, to the cell shortening twitches shown here. Now these are unloaded cell shortening computed by the model. And sort of superficially, some of those differences I just described were in fact captured by the model. If we look a bit closer though, the agreement in the shortening, the time course of the shortening, unloaded shortening, wasn't nearly as good as the agreement in the time course of the calcium transient itself with the experiments. So for example, if we look, the solid lines here, the triangles here are the model, and the circles here are the experimental results. And you can see that the difference between the endocardium and the mid-myocardial cells and the quantitative amount of the time to peak shortening was captured well by the models, and the differences that I described in the calcium handling. There was also a difference. The epicardial myocytes did reach peak shortening faster in the model, but only about half the difference between the mid-myocardial cells and the epicardial cells that was observed in the experiments was actually captured in the model. So Stewart actually did a sensitivity analysis where he looked at parameters of the filaments, which up till this point hadn't been changed for the different sites in the wall, to see if any of them might explain that additional difference, whether there may be some additional difference in the filaments that between the epicardial cells and the rest of the wall that might explain this. And the only parameter that he was able to adjust to do this was really the cross-bridge cycling rates, the ATPase. And so if he assumed faster myosin isoforms on the epicardial cells, then he actually found that the model, the time to peak shortening predicted by the model, now showed very good agreement with the experiment. But actually at the time that he did this, there wasn't any experimental data in the literature that we could find to support this in large animals. he presented this in a poster at Biophysical Society meeting, and a few posters along was a poster from Rick Moss's lab, not in dogs but in pigs, showing in fact that they did see a difference in myosin isoforms and more fast myosin on epicardial cells compared with the mid-myocardium and endocardium. So this was possibly a case where the model made a prediction before the experimental report. So this was good news. However, what we didn't focus so much on in this paper was the fact that while the sort of qualitative trend in the relaxation dynamics of the unloaded shortening was somewhat captured, highest at the longest at the mid-myocardial cells and somewhat shorter in the endo and epi, quantitatively this isn't very good. There's a 100% difference in the relaxation time between on the epicardium between the model and the experiment. And here the myosin isoform switching on the epicardium made no difference at all. Well, undeterred, we pressed on and put together a coupled model, fully coupled electromechanical model with those transmural variations in it. I'm not sure whether I need to explain this for this audience, but we have the geometry of the left ventricle coupled to some simple lump parameter model of the circulation that develops the boundary conditions. We had a high-resolution model of electrical impulse propagation, although the activation pattern was fairly straightforward. We just stimulated the endocardium and let the propagation proceed towards the epicardium in this axisymmetric model. We used the ionic model I described with the transmural variations and the modifications to the myofilament, to the myosin isoforms using Jeremy Rice's myofilament activation model, and contraction model, put it all together, solved it using an operator splitting strategy, compared the predicted three-dimensional distribution of three-dimensional strains, or specifically the fiber strain distributions, measured with radiopaque markers through the thickness of the left ventricular free wall at a site near the base here, assuming a geometry for the cell types, idealized geometry for the cell types like we show here. This is a three-dimensional version of this same model that makes for a better movie. And you can see the top are just synchronous with no impulse propagation. So really it's the bottom models that we're interested in, the coupled electromechanical models. And here we see that there are clearly differences in the strain. This is the fiber strain time course during systole. If we assume homogeneous cell properties versus a heterogeneous cell properties. And it looks in particular like the heterogeneity of fiber strain that appears in the models when you introduce the activation delay is attenuated when you include the transmural heterogeneity of the excitation-contraction coupling mechanisms. And in fact, if we take the very best experimental measurements that we have of the transmural distributions of fiber strain in the left ventricular free wall that were done by Reza Mazhari when he was a PhD student in our lab, and these are actually the fiber strains from epicardium to endocardium and the cross-fiber strain distribution from epicardium to endocardium. And these are remarkably small standard deviations for measurements made in large animals and dogs. And you can see that the pattern of fiber strain distribution across the wall and cross-fiber strain distribution in the same region of the wall in the model was actually captured quite well, both quantitatively and qualitatively, at end systole. And unfortunately, Reza didn't actually do the very painstaking measurements that he did in this study throughout the time course of systole. And so we had to refer to some later work that I don't think honestly was as carefully done. Certainly the variations were larger. To look at the time courses, to compare with the time courses of fiber strains during systole. But this is really where I want to take off on the new work, because so here, and this is back to the idealized model. This is a randomized distribution of cell types, and here is the heterogeneous distribution of cell types. And you can see that the heterogeneous distribution definitely affects the time course of strain during systole, even though it's at end systole there's no difference. Okay? So there is definitely an effect on the time course of strain during systole. However, and neither model looks like either these experiments or other experiments, and it's hard to be very quantitative about what looks good and what isn't because of the comparatively large variability in these strains. Okay. Now, take into account that these strains are not very large. So this is 10% shortening, and this is 5% lengthening during systole. And so it's not that the measurements aren't particularly accurate, it's that the strains are fairly small, and to resolve these strains at very high resolution, let alone to control for variations in the region and the hemodynamics in the dog and all these other factors, I think means that it's probably going to be hard to get data of high enough fidelity from statistical groups to compare with these type of measurements. So we might have to go to individual subject-based comparisons. But regardless, it's hard to say that this model represents an improvement or even looks particularly like these experimental results. So all of the models that I'm aware of that people have used to make coupled electromechanical models, they have to be models of calcium twitch dynamics at a minimum. And whereas there are other more mechanistic models of steady state behavior, these models of calcium twitch dynamics developed over the last 15 years or so are all phenomenological. They're not actually based on they're increasingly more mechanistic in detail, but they're not actually based on a structural model of the allosteric interactions that give rise to myofilament activation. In fact, Jeremy Rice has gone so far as to conclude that ODE-based models can't capture the essence of cooperative dynamic myofilament activation because of the nearest neighbor interactions along the thin filament on the sarcomere. And so his model is phenomenological by design, an ODE model. Well, what we're trying to do, and we haven't finished, but what we're trying to do is to develop essentially a Markov model of the thin filament activation that will capture the basic structural mechanisms so that we can start to ask questions about regulation, about the effects of mutations, so that we can start to identify parameters based on a wider array of structural information. So that's the goal, but it's a goal that those who've tried have so far said isn't possible. So what are some of the properties that we expect this model to be able to do? By the way, I should say that these models are remarkably good. I had to work hard to find these examples of results that don't recapitulate what we see experimentally. I should also say that I'm sure I've benefited tremendously from the assumption that being the student, that I was the one who really did the work on the so-called HMT model, but nothing could be further from the truth. In fact, Peter did all the work while he was on sabbatical with us in San Diego, and I just discussed it with him over lunch. So that was about my contribution to this model, was those lunchtime discussions. That model has been updated by Steve Niederer by a physical journal. And there are some other more recent models that have some interesting characteristics. So I certainly don't wish to imply that these models aren't both useful and based on a lot of mechanistic and empirical information. But in the end, they're all somewhat phenomenological, particularly with respect to this property, the cooperative activation by calcium of thin filament. So some of the basic properties that we want to be able to capture in the model is in the steady state activation of the filaments, the fact that the thin filament switch is very steeply cooperative. And so here we see measurements from Peter de Tomba's lab, where you can see that over a narrow range of calcium, the force generation goes from 0 to maximal, with a Hill coefficient of as high as 7 or 8. So a highly cooperative force-calcium relationship. Interestingly, if you actually fit Hill curves to these experimental relationships, a single Hill coefficient doesn't do as well as 2, so there's some asymmetry in the shape of these curves, such that in the low calcium regime, the actual, the parent Hill coefficient is more like 9, and then above the EC50, it's more like 5. Okay, so that asymmetry is a frequently observed characteristic of the steady-state force-PCA relation. Then finally, a critical feature of the cardiac muscle thin filament activation that underlies the Frank-Starling mechanism is that as the sarcomere length is increased, the EC50 is decreased, or the PCA50 is increased, so that the affinity of the filaments for calcium increases. Okay. So this length-dependent calcium sensitivity is a critical property of cardiac muscle that we eventually need to be able to capture in this model because it underlies Frank-Starling. The rise in maximal, on the other hand, is easily explained by the change in filament overlap, according to some studies by Henk de Kers. Now, another property, a dynamic property of calcium contraction coupling that a lot of experimental workers in the field use is so-called KTR, which is the rate of force redevelopment following a short muscle length transient designed to dissociate cross bridges. And notice that KTR, the rate of force redevelopment measured during this exercise, is steeply dependent on calcium. Okay. Interestingly, Ken Campbell, who does a lot of these experiments, has also observed that if your motor is critically damped, or the damping of the motor that you use to perform this transient will affect this result, and if it's critically damped, you can get much more reliable measurements. And one other property that he's able to extract from these experiments is this residual force here prior to the start of cross-bridge reattachment. And this residual force actually tends to correlate quite closely with KTR. That's another property we hope to be able to capture. So next is, so we've gone from the steady state to the transient behavior. So now in the fully coupled twitch, some of the properties that we expect to see in the model is in particular that the dynamics of the twitch relative to the calcium transient is such that the rise of force is actually slower than the rise of calcium, yet that the fall of isometric force, okay, is actually faster than the fall of calcium. So that can be explained in part by the cooperative steady-state relationship, but this is an important characteristic that a model should achieve. In a typical isometric experiment in cardiac muscle, if you hold the muscle length constant and it's a nice healthy muscle and you stimulate it, it'll stretch the tethered damaged ends of the muscle and shorten in the middle. So if you want a true isometric experiment, you actually have to have sarcomere length control and stretch the muscle during the twitch to maintain the sarcomere length and the middle portion of the preparation constant. And if you do that, then instead of getting sarcomere shortening in the middle with constant sarcomere length, now with constant muscle length, then with a muscle lengthening protocol, you can maintain sarcomere length constant. And when you do that, the tension, the twitch tension is higher, and the duration of relaxation is prolonged. Put another way, then, shortening actually reduces the twitch tension and the duration of the twitch. Okay. What it also does is causes some release. There's a difference between these two tracings here, so that shortening actually causes some release of calcium from the thin filaments, okay, which is the difference between those tracings there. So you'd like to be able to have that dynamic buffering of calcium in the model as well. Okay, so those are the phenomena. What about the mechanistic studies that will help us build this model? Well, one of the most persuasive and influential was this one in reconstituted filaments by Hoffman and Fuchs, where actually that's not in reconstituted, that's in I believe in intact preparations, where using 1 millimolar, or at least skinned muscles, using 1 millimolar vanadate, no, well, First of all, these are measurements of calcium bound to the thin filament as a function of calcium concentration. And then this is the effect of inhibiting cross bridges with 1 millimolar sodium vanadate. And so this decrease here has led to the observation that cross-bridge binding reduces the calcium buffering by the myofilament, has led to and I think this is the origin of this hypothesis, that cross-bridge binding actually feeds back and affects calcium sensitivity of the filament, and that underlies the cooperativity of the myofilament activation, so that as cross bridges bind, more calcium binds, and that accelerates the steepness of the force-PCA relation. Another experiment that also suggests a critical role of cross bridges is the use of soluble, strong binding, non-force generating S1 fragments that are applied to the system, and what they have the effect of doing is activating additional force at low calcium, even at PCA 9. Okay? So there is some calcium independent force that can be recruited by cross bridges that are themselves not generating force, suggesting again that somehow the attachment of cross bridge at one regulatory unit may be affecting a neighboring regulatory unit that is able to generate force. So that's together we would call this cross bridge RU cooperativity. So the cross bridge influencing the regulatory unit. In fact, we didn't come up with that nomenclature. Razumova did. The other type of cooperativity is between adjacent regulatory units due to tropomyosin overlap. So tropomyosin polymerizes end-to-end along the actin filament, and to investigate whether this could have some influence on the cooperativity of force generation or calcium binding, some studies have been done. This one using non-polymerizing tropomyosin and looking at S1 binding to actin, you can see that these non-polymerizing tropomyosin mutants have reduced cooperative binding of cross bridges. And here another way to do this is to use in reconstituted systems is to use mini thin filaments. So thin filaments that are not connected to neighbors, and compare them with that are single regulatory units in effect, that compared with a normal sarcomeric thin filament which has nearest neighbor interactions and tropomyosin overlap. And here we see, using a fluorescence measurement of calcium binding to the filament, that the use of these mini thin filaments actually abolishes the cooperativity of calcium binding, of troponin activation. So what are the structural underpinnings of this? Well, there's a lot of literature, and this paper alone is remarkably complex, as well as another one this group published later on tropomyosin. But just to orient you, this is troponin C on it. So here, these are actin monomers in the background. This is troponin C, which is the calcium binding subunit of the troponin complex. Okay. This is the C terminus of troponin T, the tropomyosin interacting subunit of the troponin complex. The N-terminal end, this is the globular part of the troponin complex. The N-terminal end forms the tail portion that extends off the screen here and interacts with the thin filament mostly through tropomyosin by stabilizing tropomyosin. Okay. And then the blue domain here is troponin I, which is the inhibitory subunit of the troponin complex. Well, the current model, and I should say that this is derived from studies, structural studies, a combination of NMR and cryo-electron microscopy studies done in skeletal muscle troponin and skeletal muscle actin, not cardiac muscle. But the current model goes something like this. So calcium binding to troponin C, okay, causes opening of the N-terminal domain of troponin C such that this switch region here on troponin I can bind to troponin C, in turn promoting dissociation of this neighboring inhibitory region from actin. So now when troponin I is displaced from actin, tropomyosin can shift over. Okay? And that causes the whole structure to change conformation in the presence of calcium from this angle to this angle. Okay? And there are experimental techniques that have been designed to measure these angle changes using fluorescence polarization. There's a whole bunch of other highly complicated stuff to do with this mobile domain. This cysteine at 133 is a sort of considered a key location on troponin I that has been used to try and build these models together to combine the cryo-EM and the NMR structural studies. What about tropomyosin? So as I mentioned, tropomyosin polymerizes end-to-end along actin with about an overlap of about 8 to 11 residues. It's stabilized by the N-terminal end of troponin T, and in fact, that's a region that contains a number of troponin T mutations that are associated with hypertrophic cardiomyopathy. So the current model for tropomyosin, or the sort of minimal model for tropomyosin, is that it exists in 3 states. So the blocked or blocking state where cross bridges can't form. Okay. The closed state that we just described that's induced by calcium binding to troponin C, so the C state stands for calcium-induced or closed. And then the open or M state, the myosin-induced state, where when a cross bridge binds in the weakly bound state and transitions to the strongly bound state, that it locks tropomyosin in that open position. So that's the model of tropomyosin that we use. So here are our assumptions that we use to formulate our model of a single regulatory unit. So first of all, calcium binding to troponin C induces transfer of troponin I from actin to troponin C, like I showed you, and dissociation of calcium reverses that transfer. Okay? Provided tropomyosin isn't in the way. Okay? Tropomyosin can only transition from the blocked state to the closed state when the inhibitory region of troponin I is dissociated from actin. Okay? And tropomyosin must be in the blocked conformation before troponin I can rebind actin, and therefore calcium can dissociate. Okay? So this together is known as the tight coupling premise, which I think was introduced by Robinson. Okay? Then in addition, we assume that strong binding of myosin, S1 myosin, places and holds tropomyosin in the open conformation. As we'll see later, we need to assume that there's only one force-producing cross-bridge that can bind per regulatory unit, which, based on the thick filament structure and the regulatory unit consists of 7 actin monomers, that seems like that's a common assumption. Okay. So actually, all of this simplifies to a pretty straightforward model. Okay. This 4-state model, which really is just a simple extension of McCulloch and Jeeves's 3-state thin filament model, where we have two blocked states, one in which the inhibition by troponin I has been removed. Okay. Then we have the closed state C corresponding to the tropomyosin transition, and then the open state corresponding to strong cross-bridge formation. So we didn't even need weakly bound cross-bridge, more than a 2-state cross-bridge model for this particular analysis. So now we end up with 6 rate constants that we estimated for various conditions: skinned or reconstituted filaments and intact muscles. Okay. Okay, so now things get a little bit more interesting because of the effect of tropomyosin on nearest neighbors. And so if we consider now a tropomyosin that's in the closed state and its 2 neighboring regulatory units, we can construct 9 possibilities, and then if we assume that one side is no different from the other, that reduces to 6 pairs of on-off rate constants that we need for RU activation once we take into account immediate nearest neighbors. So that's a total of 12 parameters. notice that we're not worrying about the calcium-bound state. We're just worrying about the whether the tropomyosin is closed or open. Okay, so the cross-bridge interaction itself is independent of this, but the cross-bridges could affect the whether whether there's a transition from blocked to closed of the neighboring tropomyosin. The calcium activation we can take care of from now on by defining a parameter phi, which is the fraction of blocked regulatory units that are free from troponin inhibition. So the fraction of blocked regulatory units that are in the B1 state as opposed to the B0 state. Okay. So surely by now we have gazillions of parameters and no chance of identifying them. Well, not quite, because what we can do is we can assume microscopic reversibility within loops within the network, and then that will generate constraints. If we assume that the equilibrium position of a tropomyosin is one where one of its neighbors is blocked and the other one is closed, so it's kind of like I'm at a concert and one kid my kids are holding my hand, and one's sitting down and one's standing up. Okay? That's my equilibrium position. But then, if both are sitting down, then I'm not going to be able to stand up. If they both stand up, then I have to stand up. Okay? So so the equilibrium position is this one. Okay? Then we define. So far all we have is the 6 constants that we've already defined and 2 extra parameters. So one of them describes the strength of that nearest neighbor coupling, regulatory unit coupling, which we call gamma. So you can see, for example, when we take CC now, so this means that the 2 neighbors are both in the closed state, then the transition rate is increased by gamma. There's another parameter in here, which is mu, which describes the sort of additional contribution that comes if one of the neighbors happens to have a cross-bridge bound. Okay? And this comes from some of the earlier work that suggests that cross-bridge binding affects activation of the thin filament. And we don't assume that cross-bridge binding affects calcium binding because there's no evidence to directly suggest that, no structural basis for that. So we have 2 cooperativity coefficients, one representing RU cooperativity, one representing cross-bridge RU cooperativity, together with our 6 constants. Okay? But we have one more thing to do, which is, of course, there are multiple energetic states of the thin filaments that this can now lead to, and how are we going to manage this? So what we do is we assume that individual regulatory units are coupled together in a loop, and we show the example here, assuming that those loops are only 3 long. Now, there are 26 regulatory units on the thin filament, so 3 is unlikely to be enough, but when we start to do more, you can imagine that the diagram gets pretty big. I haven't shown the mu's on here, but simply by making this assumption, it's possible to derive all the transitions using the parameters I've already described. In this example, where you have 3 regulatory units, it gives rise to these 10 states with 12 transitions. Note that calcium binding is not being communicated between the neighbors. It's just that the 2 types of cooperativity are just the 2 that I assigned, and we've sort of assumed a periodic boundary condition by wrapping these around in a loop. Okay. Of course, the problem is that as we increase the number of regulatory units in these closed loops, the number of unique states, the number of possible states we get grows dramatically. The number that are unique, and by the way, we generate these equations automatically. We don't write them out by hand. For example, with 9, which happens to be the number that I'm going to show you results for, we're actually up to 1,200 states, okay, and 6,600 transition rates that we compute. Okay. So this is sort of a biggish model, I guess, for multi-scale modeling, but it's still an ODE model. Okay. And the question is, how does it converge? And most of them, by most measures, converge. Well, if gamma is 1, so if there's no regulatory unit interaction, they're all converged immediately because that's the basis of the coupling. As gamma increases, the number that we need in order to get converged behaviors, and here we're looking at the Hill coefficient and some other measures of the steady state and transient behavior of the model. You can see they're mostly converged by 9 or 10. A couple of these coefficients, a couple of these results, these are Hill coefficients that are fitted to the lower and upper parts of the curve. That part of the apparent lack of convergence there is probably due to the fact that the hill curve doesn't perfectly fit the model. So in some sense, this is probably underestimating the convergence. Okay. So here we perturb the model, and the most obvious thing that we see here is that if we have no RU cooperativity, then we abolish cooperativity of the steady state force PCA relation, and we do not get steep dependence of KTR on calcium. Interestingly, though, the crossbridge RU cooperativity has almost no effect. So this leads us to conclude that crossbridge RU cooperativity is not the important component of this model. It's RU. Changing the equilibrium constant for calcium binding shifts equally the force PCA relation and KTR, and this is in agreement with studies on troponin C mutants, and similarly in agreement with studies on tropomyosin mutants, increasing the equilibrium constant for tropomyosin conformational change not only shifts the relationships by an equal amount, but increases the Hill coefficient of the relationship. And finally, increasing the duty cycle of the crossbridge cycle increases the cooperativity as well as the maximum force, but doesn't affect KTR. What if we simulate the mini filament experiment where essentially we just eliminate the nearest neighbor interactions? Well, this is without any special curve fitting. You can see making that one change captures experimental results that have been published using fluorescent sensors with the mini thin filaments. If we use the NEMS1 subfragments, those soluble non-force generating subfragments, which we can put into the model by just randomly populating cross bridges without having them contribute to force generation, then the alterations in the force PCA relationship that I described before, and to a pretty close approximation in the KTR, are actually captured by the model. Notice down here the model doesn't do so well. If you increase the number of interacting regulatory units in our loop, this curve comes down steeper and steeper. But we get down to a range here where measurements can't be made. This is some studies that Ken Campbell did that we've put in this paper of effects of inorganic phosphate by increasing the cross-bridge dissociation in our model. And here again, you see the changes in the steady state and the KTR behavior, as well as the correlation between the residual force and the KTR are remarkably well recapitulated. Now, there was no fitting at all in this result. All we did was assume, I failed to mention that we actually have two different states of troponin with bound calcium because as that complex moves, the troponin C moves along with troponin T. And if we assume that a plus or minus 1 angle for those two states and predict fluorescence polarization measurements, you can see that the model does in fact produce this decline in angle first. So calcium is binding to troponin well before force is developing, and then as the tropomyosin starts to shift, it takes over. And so this behavior is captured by the model, and the effect of inhibiting cross bridges by turning off cross bridge attachment perfectly captured in this model with no fitting. This just explains how we did that. In the interest of time, I'll skip. But here, if we look at the difference with and without cross bridges and take and subtract them, you can see that we get this sort of sweet spot where cross bridges do potentiate activation. And that, remember, this result here looks very much like the Hoffman and Fuchs result that I showed you before. This is a little bit more subtle, so perhaps I'll skip it, but the conclusion is that tropomyosin coupling means that almost all the forced activation of the filament is due to calcium when there's no coupling. But when there is RU interaction, then in that sweet spot, in fact, there becomes a strong component of cross-bridge dependent filament activation. Here we get to twitches, and so this is a twitch produced by the model in comparison with experiments from Janssen and Tatomba. And this is a steady state curve fitted to some experiments done in intact muscles that were treated with ryanodine and CPA. And here, if we look at the calcium dependent, the twitch dependence of those twitches, you can see Not quite so good agreement, but probably just not because these aren't sarcomere length controlled experiments. Just one more. So this just summarizes the effect on the twitch of our interactions. And so you can see that here's our model driven by a calcium transient. If we take out the tropomyosin-tropomyosin interaction, we see that you get a smaller peak, a faster time to peak, and a higher basal tension. And if we take out the cross bridges, you see that you get a smaller peak and a shorter twitch. So these findings suggest important roles for cooperativity in shaping the twitch, which was really the question that I came up with in the beginning. So in summary, tropomyosin-tropomyosin overlap appears to be the principal cooperative mechanism in the attacked filaments. Cross-bridge RU interactions are much less important. The effects of cross bridges on activation are enhanced by tropomyosin-tropomyosin overlap, and these findings are consistent with some recent experimental studies on cooperativity. Cooperative myofilament activation helps cardiac muscle to relax completely without needing calcium-free conditions. We still need to account for changes in filament overlap, but simplifications, importantly, can reduce these 1200 states to about 46 because most of them are hardly ever occupied. I'll just show you quickly a story about the regulatory light chain to apply this. We wanted to see if we could do something with this, and so regulatory light chain phosphorylation causes greater range of myosin movement and has been seen to change thin filament sensitivity. So does this explain, can we model this? The other thing is that in this mouse, there's a spatial gradient of light chain phosphorylation that's been seen across the wall of the left ventricle. It's high on the epicardium and low on the endocardium. And it's been suggested that that affects torsion. And so we were able to test that hypothesis in a mouse model in which serines have been substituted with alanine on residues 14 and 15, so they become non-phosphorylatable. So just real quickly, here's the experiments from Rick Moss's lab on KTR and force PCA. This is the model when we adjust the myosin attachment and detachment rates, assuming that the S1 head is now more flexible. If we put that into a model of torsion that takes into account that gradient across the wall, then you can see that compared with a model with no phosphorylation or no gradient, that it increases slightly torsion in a model of the whole ventricle, but not very much. So was this prediction any good? Well, we did an MRI study recently in measuring torsion in these mice, and you can see, in fact, the difference wasn't very great. So that original paper in Cell really that suggested that torsion was mediated by myosin light chain really isn't the case. But the difference is actually measurable, and it's about the same as we predicted with the model. So sorry for going over time a little bit. In addition to Stuart, I want to acknowledge the contribution of Joyce, who did the MRI, Sarah, and Ju Chen, who developed those mice. Thanks very much.
Beautiful work, Andrew, and beautifully presented. I think maybe Simon